So, the last class I had mentioned that about the Tromp curve, it is popularly known as partition curve. Okay. So, what is the beauty of this? Now, imagine that I have got, again I am coming back to that example, that 1.5 millimeter screen, but even 1 millimeter particle, what is the level of difficulty it has faced in getting reported to the undersized material. So, for each particle size class, what is the difficulty individually they have faced while getting separated according to their sizes. So, if we take all the size classes together and if we plot them into a form of curve, so that is what Tromp has proposed. Now, here how do we do that? Now, we can refer to any characteristic in the feed or any other stream in general terms as characteristic I or any characteristic size, okay, where I can refer to a size interval for size separators. It may be your say grade for your mineral separator. So, this is a size separation device. So, here we can refer that I as your can refer to a size interval for size separators. The amount of misplaced material, what is the meaning of misplaced material? That means, if I have an oversized material into the feed, ideally they should report to the overflow stream into my screen. If I have undersized material into the feed, they should ideally report to the underflow stream, but they may be misreporting, that is your some part of my undersized material they are getting reported to the oversized, that is called the misplaced particles, that means they are in the wrong stream. So, the amount of misplaced material to an output stream is referred to as the partition coefficient. You will get to know it clearly when we solve an example. Okay. And this is also called the distribution factor or probability factor. It is simple. Say suppose if I have an aperture of 5 millimeter and if I have a 0.5 millimeter particle, whatever the difficulty it will take, it will have to pass through that 5 millimeter, will it be similar that if I have a 4.8 millimeter size particle? No, the difficulty levels are different. So, this is what is their distribution of the difficulty they have faced, that is what is being quantified as partition coefficient. So, the partition coefficient is defined as mass of material of characteristic I in a stream divided by mass of material of characteristic I in the feed. So, it is the same concept, that is what we have observed, what we have discussed in the oversized material efficiency definition or undersized material definition, but here we are taking into consideration of each particle classes you have in your feed. It is not a single oversized or undersized. So, we can report it as MIS, that is mass of material of characteristic I in a stream and then mass of material of characteristic I in the feed. The stream could be overflow or underflow. So, that is MIF. Now, with the example, I think that it can be explained in a proper manner. If I put some numbers, then it will be easier for explanation purposes. That is why I have straight away come to this problem. Example, the size fractions of a screen oversized and undersized stream sample are given in the table below. That means, the size analysis of the screen oversized and undersized are given. So, we have taken representative sample from the screen oversized fraction and undersized fractions, and we have done sieve analysis into a laboratory, and that is what is being reported. Okay. And then I have to also know that what percentage of the feed was reported to the oversize. So, if I know what percentage, so I know that what percentage has reported to the undersize. So, here that value is given. The oversize represented 62.5% in the feed mass flow rate. So, that means remaining 100 minus 62.5 is 37.5% has reported to the undersize fraction. Draw the Tromp curve for the separation and determine the separating size and the probable error. I will show you how to do it, and this is very important for the performance evaluation, not only for screening, but for other separating devices. So, I am not going to discuss separately that how do I evaluate the performance of other Minder processing separator using the same say Tromp curve based approach. So, the oversize stream, we have got these sizes of the sieves. It starts from very coarse size to finest sizes, and this oversize stream, here are the mass percentages given. Okay. So, suppose I have got 1 kilogram of representative sample from the oversize fraction, and that size analysis I have done based on the 1 kilogram, and I am reporting that as a percentage of that 1 kilogram for each size fraction, what is the mass percentages. Okay. And this is the mass percentages of material into the, that is the undersize stream. This is the size analysis of the undersize stream. Okay. So, what I have to do now, that is, when I know the oversize material size distribution, when I know the undersize materials distribution, and I know what fraction of the feed material has gone to the oversize, and then I know automatically that what fraction of the feed has reported to the undersize. So, then I can calculate back that what was the feed size distribution. That means, what we call it reconstituted feed size distribution. There is a debate. There are many times people say that when we are doing this type of analysis, we should do the feed size analysis, oversize material size analysis, and undersize material size analysis, and then we should do some kind of your mass balancing based approaches to rectify these numbers. That is a little bit complex, but my argument is that is it is much better way of doing things, that is let us do the reconstituted feed, because when you have done the taken the feed, maybe that feed has not been actually sized, what you are taking it from the oversize and undersize. Because when it is a mined sample, your feed may be changing at even the say shortest time interval. So, why do I worry about that? So, let me let me go back to the reconstituted feed, that is at the time of collecting my representative samples from the oversize and undersize, what was the feed? We can get back to that. So, how do I go back? That is the your some conceptual thing you have to, some concept, your concept must be clear. So, this is the percentage of your each fraction. Now, how much of that I have got, what fraction of the feed has come to the oversize? Now, say suppose I have got a feed of 100 tons, out of that 62.5 tons I have collected into the oversize material, and the average size analysis of that 62.5 tons is this. So, if I say that how much of this size was there, how much of material out of this 62.5 tons material was there in the oversize material. So, what I have to do, that is I have to get back to the your actual mass. So, this is the percentage 37.5% out of 62.5% of my feed material. So, what I have to do? 37.5 multiplied by 0.625, that is the fraction. So, then we get back to this value. So, like that 32 multiplied by 0.625, 13 multiplied by 0.625, like that all the numbers here in this second column we have to multiply it with 0.625 to have a column like this, that is the column B, that is the mass in sample, which is being reported at a discrete sizes into the oversize. So, if I add them together, I should get back to this value of 62.5. Hope it is understandable to you, or it is clear to you. Similarly, for the undersize fraction, what fraction I have got? 100 minus 62.5 into the undersize. So, I have got 37.5% of the feed material. That means, if my feed is 100 tons, I have got 37.5 tons in the undersize material, and if I do the size analysis of this 37.5 tons of material, so that will be that will bring me back to this, that is your 0.5 into 0.375, that will give you 0.19, like that all the individual numbers which is reported in the column C multiplied by 0.375, I should create a column called D like this. So, this is very conceptual, that first what is the total feed and how they are split. So, 62.5 tons has gone to the overflow, remaining 37.5 tons has come to the undersize. That 67.5 tons consists of how much of plus 17889 microns. So, that is 23.44 tons. Like that we are basically discretizing it. So, if I now go back, that how much of that material of plus 17889 micron was there in my feed. So, that will be 23.44 plus 0.19, so that means 23.63. So, the column E is equal to B plus D, that is your B plus D. So, you get 23.63, like that if you add column B plus column D, you get these numbers. I strongly advise all of you to kindly practice this. Even you can practice this with these numbers, and best way to practice it is through my Excel, PowerPoint, or maybe you can use a calculator. These are all simple arithmetic calculations. Okay. So, now I have got this feed. Now, according to Tromp, the partition coefficient for each size fraction is basically, if I can do it based on your undersize, or maybe I can do it based on oversize. So, if I do it based on oversize material, it is B by E, that is what percentage, what is that total mass I had, which is plus 17889 micron, that means coarser than that. So, that is I am getting 23.44 tons of material into my oversize fraction out of how much? Out of 23.63 available in the feed. So, the partition coefficient is F is equal to B by E. I can similarly do it with your say sample your say D by E also for undersized particles. Okay. So, that will give you 0.99. So, that means for the coarsest particle, the effectiveness of the screen is around 99%. But you look at, as you are going closer, as you are going down. So, similarly for this size it is 0.98. Now, you are getting different values for that. So, this is giving you that what is the difficulty this your screening operation has faced for each discrete particle sizes. Now, if I plot them, that is your mean particle characteristic, that is I can plot it based on size, this is a size separator. So, I can plot it based on size, and if I have done the discretization based on specific gravity, I would have plotted it in the x axis, that is your specific gravity. That is what we do it for gravity concentration processes. So, here it is the mean particle characteristic, here it is the size, and we have taken a logarithmic scale, so that we can have a spread of the data. And then this is the partition coefficient. So, for each particle sizes, what are the difficulties being faced? If I plot them and the difficulty is represented by the partition coefficient, we get a plot like this, and this is what is showing, that is the your coarser particle are having your say less difficulty of separation, but at what size? What size you have separated? So, that is a critical issue, that is we have not specified a size. So, here the Tromp's suggestion is that you take D50 size. That means, normally it is a practice now, when I plot this curve, which is got a typical shape. So, then the D50 is the imaginary size, where there is a you have got 50% oversized material at that size, and you have got 50% material into the underside. So, this 50% data, that imaginary size, you are getting it from your partition coefficient data. It is not the actual separation which has given you. So, if I have, so if this is my imaginary size, so suppose this is 200 micrometers, and if I have separated, if I have obtained this data at an imaginary size of screening at 200 micrometer, I would have got 50% material into the oversize and remaining 50% of the feed material into the underside. So, now there is another concept here, that is your called Eckert probable error, and this is defined as, that is if I have an ideal screening at 200 micrometer, I should have a curve like this, I should have, instead of a curve, I should have a vertical line like this, and all my oversized particle should have been having a your partition coefficient of 1 or 100% efficiency of separation, and all my undersized particle should have efficiency of separation of 100% or your partition coefficient of your 0. So, that means, I should have a vertical line instead of this curve. So, now the concept here is that in actual operation I have got this. Please remember that this definition is based on that D50 concept, that what is that imaginary size at where the screen has given me a 50-50 split of my oversized and undersized particles. So, similarly, from this also I can calculate what is the 75% passing size, D75. So, that is the D75 I can calculate, that is your material where it has got a split in between 75:25 or your 3:1. Similarly, I can get a value of D25, that is at 25% here, that is your 1:3. Now, why should I take D75 and D25? Why not other values? If we look at closely, that within D25 and D75, it is not a curve, it is almost a straight line, but it is beyond these two values, there is a some deviation in the your the curve. So, I have got a straight line. So, when I have a straight line, so basically this concept has come from the slope of this straight line, but I am not getting into that detail. So, this Eckert probability or probable error is defined as EP is equal to, in short form we write it EP, that is Eckert probability, or we call it probable error also, the D75 minus D25 divided by 2. And there is also another definition, it is called the imperfection. This is also the same thing what I am saying, but it is showing the area enclosed under this, that how much is the deviation from the ideal curve. So, imperfection is defined as D75 minus D25 divided by 2 D50. So, these are the two basic changes in the definition. Here you are dividing it also by D50 sizes. So, now if we go back to that data and if we plot that data, so we get a curve like this, that is with your mean size versus your partition coefficient, and you get a separation size D50 is equal to 2800 micrometer. So, here the D50. So, the previous curve was not drawn based on the data given. This is the curve drawn based on the data given. So, here the D50 is 2800 micrometer and the D25 is somewhere here, it is around 1200 micrometers, and D75 is somewhere here, which will give you the value of 6600 micrometer. So, now the efficiency EP is equal to D75 minus D25 divided by 2. So, that is 6600 minus 1200 divided by 2. So, that is 2700. So, that means it is the Eckert probable at this is 2700, but as because there is no upper limit for this, it is very difficult to assess that whether my screen is doing my job in a proper manner or not. But I suggest that for screening, this is a imperfection is a better way of doing that. So, your if I look at that is your imperfection is nothing but your EP divided by D50. So, what is the D50 value? 2800, because it is D75 minus D25 divided by 2 D50. So, it is 2700 is the D75 minus D25 divided by 2, that is EP by D50 will give you the imperfection. So, that is 2700 by 2800 is equal to 0.96. So, if it is a perfect separation, this should have been your 2800 by 2800, it should have been the 1. So, your EP, your imperfection is 0.96. So, these are the answers to the questions. Let us look at that what are the other factors, what are the various factors that affect screen performance. That is, why do you think that the screen is not industrial screens, they do not operate in a perfect manner? So, I must know what are the governing, what are the different factors. So, screen effectiveness must always be coupled with capacity, that is at what rate we are separating. So, screen performance is affected by factors that influence the probability of particle passage, that is how much of passage you have given, what is the probability of that particle. I keep on hammering this, that how many times each particle class has got the opportunity to interact with the aperture to finally decide that whether I am finer or coarser than that aperture. So, and the factors that influence the number of opportunities the particles are given to pass through the screen mesh. So, one is particle size. So, I have already given that demonstration with the straight screen. I have shown you the different particles and how do they behave. So, the overall screening efficiency is markedly reduced by the proportion of near sized particles, that is from 0.75 to 1.5 times your size of the screen, because these particles tend to plug the apertures. Sometimes because of some projected your areas, they may get just stuck into the screen surface. So, they will not only create problem in your mass balancing, because they are not reporting neither in the oversized fraction nor the undersized fraction, but the passage is also blocked. So, with time your entire effective surface area of the screen will be reduced, and naturally your screen efficiency will be reduced. Feed rate, that is what we have already discussed at depth, that is your overcrowding, that is residence time effect, that is how much of time you are giving and what is the bed depth you are creating. So, if you are feeding at a very high rate, so the some of the particles at different layers, they may not have any opportunity to have this your interaction with my aperture to finally decide that whether I should report to the which stream. The next is the particle shape. I had shown you that if I have an elongated particle, so it depends on what is that your basically the orientation. So, that will decide finally that whether it will finer or coarser than that. So, mica for instance screens poorly on square aperture screens, because if I have a mica is a like your say flatter particles like your lentils or maybe flatter than that. So, as on a square aperture screens they get plugged. It is flat, plate like crystals tend to ride over the screen apertures, that means they will just sit over the it will not move even. So, it will block the passage. Then the open area, how much is the percentage open area you have given in the screen, and that is the challenge to the screen manufacturers, that is how much of opening area you can give. That means, one example I have given, that is if you can minimize the wire thickness, you can create more open area, but not at the expense of your maintenance or your say damage to your screen. So, you have to give prolonged life as well as maximum aperture area. So, the material scientists they play a huge role here. So, the chance of passing through the aperture is proportional to the percentage of open area in the screen material. So, we have already derived this, we have shown you that what is the open area, how we can calculate it. Open area generally decreases with the fineness of the screen aperture. Why? Now, the material gets choked, material blocks, because you have got more near size materials and the fine particles at the very fine sizes of apertures, they are very difficult to pass through. So, they plug your openings. So, in order to increase the open area of a fine screen, very thin and fragile wires or deck construction must be used, and we use also weight screening. So, that they are basically the water also tries to say flush those particles. So, this fragility and the low throughput capacity are the main reasons for classifiers replacing screens at fine aperture sizes. This is the reason, that is below a particular size the screen effectiveness reduces drastically, and that is why we have to switch over to other mechanism, that is called classifiers, where we use the principles of movement of solids and fluids to separate them. And but these days there are some developments happening in the even with the say fine screening. Okay. Screen angle, that is the slope of the screening surface affects the angle at which particles are presented to the screen apertures, because if they are inclined, you know the apertures at different locations they will be different. So, that also affects the screen performance. Where screening efficiency is important, that is I want higher screening efficiency, horizontal screens are selected, because the particle movement is slow through that. It also affects the residence time of particles on the screening surfaces, that is your capacity will be less. Vibration, you can use vibration for stratification, because it helps in stratification and reduces blinding, because the particles are always in mobile. So, you are reducing the blinding means choking of the passages of your apertures. Moisture, because if I have more moisture into my material, so the efficiency goes down with sticky materials. Bed depth, we have discussed it. The bed depth means your the how many layers you have got. So, that means if the screen surface is does not have any aperture, suppose if you have a plate, and if I am feeding that rate, what is the depth of that material. So, if the bed depth increases means the less chances of the top layer of particles to have interaction with the apertures. So, your capacity will be reduced. Okay. So, in that case, the bed depth of material on the screen affects the efficiency and the performance of the screen, and the fraction of particles in the feed stream that is smaller than the sieve openings and occupying upper layers, we have already discussed that. And agitation of the screen surface imparts fluid properties to the bed of particles to impart stratification, because when you have bed of particles and when you are trying to vibrate or lift them up, so you are increasing the volume occupied by the particles. So, the particles have got more space or the more void spaces to say to pass through that, and they decide or you are trying to give more probability or opportunities for the particles to have interaction with the aperture. This thing we will discuss more, that is the fluidization, when we discuss about one separator, that is called a jigging operation. So, the depth of the bed, the rate of feed rate and the inclination of the screen are of major importance to the screen operation. So, how much of bed depth I should have? According to Matthews, for screens of length from 1.8 meter, the bed depth at the discharge end should be a minimum of about 1.5 to 2 times the average particle size. These are some of the proposed rules, and you have to verify it that whether it works well with your material. And for spring lengths of about 7.2 meter, the thickness of the discharge end should be about 2.5 to 3 times the average particle sizes. But this is not a fixed rule, I am repeating it again. You have to verify this with your material. So, if the screen length was 2 meter and the average particle size is 850 microns, then the minimum bed height at the screen discharge end should be about 1.3 millimeter. So, this is the chart where I am giving the ratio of particle to aperture sizes. That means, when the your aperture size is suppose your 1000 micron and your particle is 1 micron. So, the ratio of particle to aperture is 1 by 1000, that is 0.001, and chance of passage per 1000 is 998. So, this is number of apertures required in path only 1, that means one passage, one chance it has got 998 times out of 1000 times it will pass through. So, this is like your probability calculations. So, whosoever is more interested to know about this, you can go through this, and this is what is showing that when the particle to aperture size goes down, that is your probability, that is your number of apertures required in path increases. That means, you have to increase the residence time of the particles manifold. So, the effect of near size particles we have discussed. Overall screen efficiency we have discussed, that is the proportion of the near size materials, and the problem is often found on screens run in closed circuit with crushers, where a buildup of near mesh material can occur and progressively reduce screening of efficiency. So, we will continue this in the next lecture. Till then, thank you very much.